Welcome to the 20th class meeting of EECE341, Introduction to Communication Systems. The first announcement is related to actually quiz 2. Quiz 2 is coming. It will be held on Monday tentatively. If you have other schedules, important schedules, please let me know on Monday during the class meeting. The format is the same as quiz 1. Homework 19 is already assigned, as many of you have checked. They are all textbook problems. So this time it is not true false. So it is not simply fill up the blanks type problem. You have to solve many problems. So I recommend strongly to start earlier than usual. Let me emphasize about the voluntary project. Nobody has contacted me yet. It seems that, hey, anybody except me, don't do that, okay? Your life is fabricated by yourself. Okay, companion courses, mathematics for EE engineers, A, electromagnetic waves, introduction to digital communications, communications and networks, analog circuits, RF analog circuits, digital signal processing, probability and random processes, etc. There are now 4 messages from me: simplification, visualization, check the uniqueness, and existence and uniqueness whenever you talk about something. Okay, yeah, I got a lot confused. Let me check. Probably I'm looking at some other calendar. Let me check just a second. Okay, so when is the Monday. Yeah, 25, I believe then. Good point. As always, sometimes I got confused that we are living in the spring semester, something like that. Okay. Corrections and clarifications. Let me talk about little bit about FM radio broadcasting. Not many of you are fans because this is no longer FM broadcasting era. But when I was in your age, most of us, my friends, were listening to the music from FM radio broadcasting. So there was a lot of signaling songs made by different stations. For example, in Korean, 89.1 megahertz was KBS1 FM around the Seoul area. And we've heard other KBS2, EBS, MBC, and there was something interesting there about their center frequency of the radio broadcast stations. They all ended up odd numbers in the first decimal point. So it's like, as you see right here, I've taken Seoul Dobong area FM radio broadcasting. Hey, it's KBS 2. Okay, my memory is wrong. So 89.1, 89.1, and then you see that all the numbers are odd numbers. Does that mean something? Does that mean something? So that's what I want to talk today. Got it? So if you Google the web, you can find very common questions like this, even in English. So a lot of Americans ask similar questions to, for example, QORA, the American version of 네이버 지식 검색. I found this one. Why do FM frequencies end in an odd decimal? And that was very good answer. And interesting thing is that the United States and the Republic of Korea, South Korea, use the same frequency band for FM radio broadcasting. And this number I memorized from my middle school, 88108. So it's 88 megahertz, not kilohertz, megahertz to 108 megahertz. This is the same. So you now have some idea. So starting frequency ends with an even number. So let's draw. And this is megahertz. By the way, when you talk about kilohertz, you must use lower letter. But for mega, you must use uppercase. So suppose you have some 88.1 megahertz station. Usually, rarely there is, but suppose center frequency is there. Then what does that mean? Probably your FM station takes up the bandwidth in real passband. How much? 200 kilohertz, right? Because this is 100 kilohertz. So 100, so 200 kilohertz. And actually, that is the answer. The band is divided into 100 channels, each 0.2 megahertz means 200 kilohertz. That's why they are separated in this way. Of course, in order to reduce the interference, possible interference, usually the channels are not allocated in the adjacent slot. However, as you see, some of them really are neighbors. See that? Here, this center frequency of 국군 방송 and that for TBS EFM has only 200 kilohertz separation in the center frequency. Got it? So this is the way. So let me say, this is FM radio broadcasting band. Okay? This is band, and each one is called channel. And there are 100 channels. Got it? So have this in mind, and then you can compare easily with the bandwidth of the AM. As you know, even the CD quality sampling rate is around 20 kilohertz. CD quality has sampling rate, which means that in baseband, our audible range is around up to 20 kilohertz. Now, suppose we use DSB family of modulation scheme, AM, then it right shifts and left shifts in the frequency domain, which means that in the passband, real passband, the bandwidth of even the CD quality analog signal, not the digital, occupies around 40 kilohertz, right? But FM occupies 5 times more. Actually, the user AM radio broadcasting has narrower bandwidth. So what people say is that it's not just 5 times wider, it's much wider than AM. That's what we are going to see. By the way, this is ITU's classification of radio frequency band and FM broadcasting band is in UHF, very high frequency. Of course, this medium high, very high, ultra high, super high, extremely high was the terminology of around 100 years ago. Now, this very high frequency is actually, we feel very low because your cell phone is working around 2.5 or 3.5 gigahertz. And your Wi-Fi is around 2.4 gigahertz, 5 gigahertz, and 6 gigahertz. So that is normal to us. However, around 100 years ago, or even 110 years ago, this was named in this way. Anyway, so have the feeling of the FM frequency bands in your mind. Got it? 88, 108 is very important number for you to remember. And there are 100 FM channels with 200 kilohertz bandwidth, channel width. Okay, there is another figure, and you can see some interesting thing. This is, I believe, highway broadcasting. So around Seoul area, FM 100.5, and you see this is for the highway traffic broadcasting channel. And something interesting occurs here. So we are living here in Yangil, Cape, and we may receive the broadcasting, the same channel actually, from Daegu station and some other station. I'm not sure, probably it's Gyeongju or I don't know. And they have different center frequency. Why? Why the same radio broadcasting station use different center frequencies depending on the reason? Why? To that kind of question, consider what if. Okay, what if is very important. So whenever you are fed, you are fed some knowledge, 주입식, 지식, then every time you are fed some knowledge, ask why or why not. Okay, so if I say, and without telling you any reason, hey, this is the figure for the TBS, is TBN, sorry, TBN stations in the South Korea. And whenever you see something like this, why not just use the same frequency? Got it? Or why they use different frequency? That these are very, very important questions you have to ask. Got it? So let me add two more. Okay. So after that, you ask what if. Got it? So what if they use the same center frequency? And suppose they transmit exactly the same information. What will happen? Suppose I drive my car from here, tuning to this station, and move to Daegu. By the way, Daegu is not the north. Daegu is southern part, actually. Pohang is more northern, located in northern part. What will happen is that if they use the same center frequency, in the beginning, the signal transmitted from this station will be much larger, and they will be tuned, and there will be no problem. However, while I drive through the Pohang-Daegu highway, there will be some points where two signals may have almost equal power. And you may say that, hey, then power 1 and power 2, let's say they are P1 and P2, then the received signal strength is square root P1 and P2. Hey, great, right? You may say that, but it is not. Because even the ideal case, the signal will have different delay, right? And they have different phase. If there is different delay, then it's similar to multi-pass channel in point-to-point communication. For example, there is a Wi-Fi access point, and here is my cell phone. And there are many obstacles reflecting the electromagnetic waves. There will be strong line of sight signal, but there will be a lot of other signals that is bounced back and forth and eventually arrive at my cell phone. Interestingly, we are sending data symbols very fast. So even though the path difference in length, in meters, is small, so it's like 300 meters gives us 1 microsecond difference in time arrival. Now let's translate. What about nanosecond? Then 30 centimeters difference that can be easily occur here gives us 1 nanosecond difference in time. And that's huge because 1 nanosecond corresponds to 1 cycle of 1 gigahertz, right? And we are using higher frequency than 1 gigahertz for Wi-Fi, 2.456 gigahertz. So this 30 centimeters or 1 meter path difference gives us a lot of phase difference between two received signals. And that makes huge challenge. And I will talk about that next time, but remember that one. We are going to study from today and probably in the next class meeting why FM is so good compared to AM. Why people love the FM. There are many reasons. And you'd better know those reasons because the reasons are still persisting in our digital modulation and digital communication period. Got it? Anyway, so last time we studied the transmitter part of angle modulation, especially with emphasis on frequency modulation. And we learned a rule of thumb called Carson's rule. We wanted to know this strange nonlinear modulation called FM or PM, how they convert an analog voice, for example, into some strange signal. So, for example, 20 kilohertz acoustic signal converted to occupies how much bandwidth in real passband. It's not easy because of this nonlinear operation. In DSB-SC, even though they are not precisely speaking linear filtering, but we call linear modulation because one of the reasons is that our bandwidth in baseband is just doubled and appears in the real passband. However, as you've seen, we in the single tone analysis of angle modulation, single tone signal have, mathematically speaking, countably infinite sidebands. Fortunately, the coefficients decays very fast, but we wanted to have some rule of thumb about what's going on. That was Carson's rule. And in Carson's rule, the bandwidth was something like this. Sorry. I even do not remember. Just a second. So let me see. So here 2 times beta plus 1 FM. So 2 times. Here it is. Yeah. 2 times. So in a single tone with tone frequency f sub m, and if we have modulation index beta, then this is the bandwidth. And this is the starting point of Carson's rule. And then Carson generalized it to general analog signal. And we had something like this. Is it W? Yeah. So W is the bandwidth of our analog message in baseband, and D corresponds to the peak deviation. That's normalized peak deviation. So let me go up and show it to you. Yeah. So as you see that the peak frequency deviation is divided by the bandwidth of the message. So this is the normalized peak deviation. By the way, let me emphasize one thing, one trick. You have to love it. So here, what is the unit of beta? What is the unit of dimension of beta? It's a unitless quantity. Why? Because it is added by 1. A number has no unit, okay? And we want to talk about bandwidth. So this is a kind of bandwidth, hertz, and this is in hertz. So these should have, all the numbers actually has, as a physical quantity, must unitless. If T is unitless, this beta plus 1 must unitless. Same happens here. This has the unit hertz or per second, and this has per second. Then D, if 2 has is unitless, D must be unitless. Got it? So it must be a kind of some quantity that is normalized by some quantity divided by another quantity with the same unit or dimension. Got it? That's why immediately I said that this is a normalized version of peak deviation. Anyway, so Carson's rule was important. And we studied 2 transmitter structures for angle modulation. One is direct method using voltage-controlled oscillator. And you've seen some fill up the blanks type questions from the previous homework. And there is another method, indirect method, which is used practically in the early age of FM broadcasting. That is indirect method. Indirect method is named because it generates wideband FM signal, but it starts with narrowband FM signal generation and use some nonlinear device called frequency multiplier to multiply some number, integer, to the argument of our cosine function. And then we use up conversion mixer so that we translate the signal to our desired frequency band. Got it? And that is kind of following again and again the idea of 2-stage up conversion. So if there is a new technology here, it has some root in the old technology. So there are overlaps. That's why you'd better understand or study some history of the current state of the art. So you are learning some kind of context of state of art, the current technology, by studying old technologies. Got it? That gives not only some knowledge, but also a lot of lessons even without living the past. Got it? Today, we are focusing on the receiver part of angle modulation, especially with emphasis on frequency modulation. So the key terminology is frequency discriminator, which in the ideal case can be implemented using differentiator and followed by envelop detector. This part, I gave you some idea last time at the almost end of the class meeting. However, in the practical case, due to some other channel impairments, we also need so-called bandpass limiter. So let me show you the structure first. So this is the most practical, however, idealized FM receiver structure. So here goes your received signal. And this signal is not ideal. So your transmitted FM signal propagates through the radio channel environment. There may exist some multipass or time varying component, such as your radio receiver is mounted in the automobile, which moves fast. So it makes the channel a linear time varying channel, or some other things like, as I told you, you may have interference from the same station possible or neighboring station, something like that. So there are some impairments. That's why here goes limiter and bandpass filter. By the way, what is a limiter? Limiter is, mathematically speaking, something like this. If this is the input to the limiter, the output of the limiter is a nonlinear mapping like this. So it's a memoryless device, and its input at any time is clipped with some level, and here goes your output. So suppose this is your signal x of t, and your signal is a sinusoidal signal, for example. Then what would be y of t when this is the clipping level? Then you have some signal. I'm not drawing correctly. Let me draw here. So you have the output looks like this. And of course, this is a nonlinear transformation of the input. Then what will happen in the frequency domain? Of course, for general input signal to a limiter, it's very hard to imagine what will happen. However, whenever you are asked such a question, your approach must be, hey, let's simplify, right? So here we have chosen a sinusoidal signal because that is one of the simplest ones. You may say that, hey, let me choose constant. If that value is greater than the threshold, then, well, you will see some constant saturated. That's too simple. So we choose sinusoidal signal, a single tone. Then this is a periodic signal, right? In the single tone simplification. Periodic signal, but it is not a pure tone. What will happen? The period didn't change. Then you must open your toolbox and find a tool named Fourier series, right? So input had single tone in the positive frequency side and negative frequency side, direct delta function. Now, after clipping, what will happen? You will see a lot of harmonics, right? You will have a lot of harmonics, so that's too bad. However, if you have a filter that only passes, for example, third harmonic, a second harmonic, or some harmonic, then you may recover the signal, or you may even have frequency multiplication, right? So this nonlinear device is one of the favorite choice of circuit designers. Whenever they have difficulty, they put some nonlinearity and then see what's going on and do some linear filtering. Now, suppose you have this bandpass filter centered at the same frequency. Then you may say that, okay, then the output output would be a single tone having the same thing. And you may say that, hey, it's a just scaled version of input. What's the use of this? But let's go back to our original assumption. Suppose you had amplitude variation or envelope variation to the input signal. So your sinusoidal signal is actually attenuated. Suppose. Then what will be the output? So this signal, if the clipping level is around here, will be nonlinear transformed, right? Which means that you have a lot of harmonics. However, if your filter passes only the first harmonic, then you may recover this signal. So here you have a front face with big question mark. Why we do this stupid thing? But now you are smiling. Something interesting happened. Even though we have amplitude variation, this limiter and carefully chosen bandpass filter may remove this variation, right? Now, we need a LiPo phase. So this inverse means we generalize and further generalize. Suppose our received signal, input signal to the limiter, is some FM signal with amplitude distortion. And the reason, don't ask right now. So it's no longer zero crosses at the single period because every angle modulation actually changes the zero crossing distance or spacing, right? In a way. However, after limiting and bandpass filtering, what will happen? At the output of the limiter followed by bandpass filter. And you may, it's not exact, but there are some distortions. However, these zero crossing points are almost preserved. Got it? So these spacings are not exactly, but almost preserved. And you can easily guess that, hey, we may have almost constant envelope signal. So actually, we are recovering our transmitted signal, even though the channel have distortion on its amplitude. Got it? So this, not this one, sorry. This pre-processing, right, removes amplitude variation and introduces small, of course, distortion. However, in FM, we want to remove amplitude variation because this is our idea of FM receiver. So as we've seen last time, if we have removed any amplitude variation or we didn't have amplitude variation in the FM or AM received signal, if we can build some system that does a mathematical operation called differentiation and followed by envelope detection, then we can remove the message signal from FM modulated signal, right? However, at that time, we assumed it had the input to the differentiator had no amplitude variation. That's why the argument inside the cosine function is differentiated and comes out. So let me write it again. So last time, suppose we have ZR equals some A cosine 2 pi FCT plus phi of t, then our differentiator gives what? Some signal like this, right? And we converted it to a complex envelope form and found the complex envelope and took the modulus or absolute value. So if we can build ideal envelope detector, then we have here output some constant times 2 pi fc plus d phi dt, right? In order to have this, we needed what? Constant. If this is some a of t, then we have what? This times that one, right? So this differentiated times that one plus this times differentiation of cosine function. So we cannot obtain the desired signal at the output of envelope detector if there is some distortion in the amplitude. That's why we have limiter followed by bandpass filter here. Got it? So now you see the interplay between the simplification, mathematical simplification, and some feedback from your left side building. Hey, we measured, and it seems that there is some amplitude variation. Your differentiator followed by envelope detector idea, mathematically true, but it's a nonsense. And then what do? You devise another mathematical idea as this. Hey, suppose we have a limiter and bandpass filter, then even though there is some distortion, we may get back our original assumption, constant envelope signal. Got it? That is the idea. So this figure becomes the idea, but the problem is that still it's the idea on the right side building. In order to really implement this mathematical idea or mathematical procedure, you need some state-of-the-art circuit design of your period. In the early stage of radio communication, there was no digital something, all analog. That's why people devised many different receiver structures using different circuits. I'm not going to cover that. If I were a circuit theory guy, professor, and teach this course, I will put more emphasis and most of the time to tell you how this mathematical idea can be implemented using circuits. But I'm not majoring in that, so I'm not going to tell you much about that. But let me show you some little bit. So the first thing is how to build a differentiator. So limiter followed by linear filter may be easy, right? You may use some nonlinear device, and suppose that's done. So differentiation. And you may say that, hey, simple inductor differentiates the signal. And of course, there are other ways. And other ways are motivated by, again, the mathematics. So if you choose very small time delay, or you may have some path with small delay and you subtract, what will happen? What is the derivative of a function? It's a limit of what? The difference in the signal variation divided by time difference, right? So this actually is a good approximation to a differentiator. So you may build your differentiation part like this, and you may check whether your output quality is satisfactory or not. If it is satisfactory, you are done. Otherwise, you have to have different idea. Envelope detector, I'm not going to talk about it because in the AM receiver, we already had it. And let's assume that is already given. So this is one of the idea. And another idea is like this. So we use some RC network, not the inductor, because inductor is a coil that gives us a lot of pain usually. And even though you need inductor, sometimes it can be implemented using capacitor and vice versa, as you know in the circuit theory. So we use this RC circuit, and this RC circuit has interesting property in the frequency domain. It has up to RC constant. The magnitude response is kind of linear. And if our center frequency is located here, this magnitude is an affine function. And we need as a differentiator, so what is the frequency response of differentiator? If we view the differentiator as a linear time invariant systems, we have the frequency response like this, right? J to pi f. So if we take the magnitude response, you will see something very similar to it, right? So it's linear, and you have some time scaling coefficient, right? So you may say that, hey, that's good. However, be careful. We need to differentiate the signal, right? And we didn't want some distortion in phase, right? So here, as you see that, the angle is fixed. However, your circuit introduces not only the magnitude response, but also phase response that is not constant. So what do we do? So these circuit design guys invented many, many other ideas. And also, if you read the textbook carefully, it's not easy to have very sharp slope here. So they devised some ideas like balanced discriminator, which I have no idea. And they have something interesting here. Once I told you in this course and in the other course that people compiled the history of great inventions, and they wanted to extract some common features. And the Russians, the Soviet Union guys, did that very well. And also now a lot of Japanese, Koreans, and even Americans do something similar. And they have found is that the key is what? Replace the scarce resource of your problem with an abundant resource. And to do that, sometimes you think about what? You add two different ideas. You subtract, you remove some already existing, very expensive or cumbersome operation. Or sometimes you have a single pipe. What about have multiple pipes? If you have single big pipe, what have small many pipes? So this arithmetic type idea, add, subtract, multiply, and divide, had given us very good result. And here goes something similar. And this balanced discriminator is something like this. This does not work well. Even though it's a good idea, we cannot easily get very small, a very large number in the slope. Hey, what about having two of them with slightly different configuration? This is the idea of balanced discriminator. And actually, it removes a lot of problem here. Suppose your objective is to build a good approximation to differentiator idea. And your stage of technology can build this type of circuit, no problem. But performance of this one is not good. What do? The cost of having this circuit is very small. Then what about having two? What about having three, right? So they put almost the same structure. Of course, that's different. But anyway, you see here, multiple RC parts, and you can see that the almost symmetrical upper branch and lower branch. That is the idea. Okay, so I've taken some explanations from the textbook, and that is the idea. Anyway, so these are some crude ideas, and another is to use so-called phase-locked loops in the receiver. Of course, this is for, at that time, for an expensive FM receivers. For non-expensive ones, they didn't use phase-lock loop. And phase-lock loops are widely used even in today. And there are many applications. And if you take some analog circuits course, sometimes your professor spends a lot of time to talk about PLL. And I'm not good at it. And what I want to just say is that the phase-lock loop is related to the voltage-controlled oscillator. So voltage-controlled oscillator is a device where you apply some signal, then your output is something proportional to your frequency is proportional to the input. This is voltage-controlled oscillator. The problem is that this voltage-controlled oscillator itself, as your operational amplifier does, just a single device has not much application. When it is equipped with some feedback loop, then it does a lot of interesting things, as your operational amplifier did in your circuits course, right? Operational amplifier was what? Took the difference between the two inputs and hugely amplify the output, right? And you may say that, okay. And even your textbook says that even though a manufacturer generates the same model of operational amplifier, if you really measure the gain variation is huge because its value is very large, 10 to the 6 sometimes. Then what's the use of that kind of imprecise amplifier? But interestingly, if you connect some resistors with feedback, then suddenly you can stabilize and have very predictable gain of that amplifier. Similarly, voltage-controlled oscillator with proper feedback can be an amazing device. So let's see just some figures because I'm not a PLL guy. So here goes nonlinear phase-lock loop model, and here goes linear phase-lock model. I'm not going to talk about details because even I do not remember, and actually I even never had complete understanding about PLL. So I'm not going to ask you today. But remember, what is important is what? This feedback. Got it? So here goes your some desired signal, and output is fed back. Again here, same thing happens. Got it? So this feedback makes not only the voltage-controlled oscillator, but also, not only the operational amplifier, but also the voltage-controlled oscillator, very, very useful. Got it? And if you want to study that more, then interestingly, take automatic control course, because that course is almost all about feedback control in your undergraduate course. Got it? So I'm not going to talk about it. But let me talk about the Costas loop. Our textbook says Costas PLL, but it's more referred to as Costas loop. And Costas is the last name of the inventor, of course. And this Costas loop is a very interesting system. Here goes the voltage controlled oscillator we talked about, right? This is now used for demodulation of a real bandpass signal. So here goes our real bandpass signal. And for convenience, just we assumed AM signal. Let me say DSB SC signal for simplicity. And you see that this is sometimes called product detector. Sometimes called this is product detector. But in modern days, it's called IQ demodulator or quadrature demodulator. And I prefer the second one. And you see that here is the output of voltage controlled oscillator. It's some kind of cosine signal with possible frequency offset from your desired frequency, and even some phase noise. As our operational amplifier itself may have a lot of error in the gain, voltage controlled oscillator itself may not be that precise. However, anyway, here goes the signal, and you can build, I don't know how, but you can build a phase shifter for low frequency, not that high, some gigahertz, but low frequency signal. So here goes cosine signal, generated the voltage controlled oscillator, and here goes the sine signal. And you multiply. These are product devices, right? Or mixers. So these are product devices or mixers. That's why this structure is called product detector. And as you remember, here goes low pass filter, because if these frequencies are almost the same, you down translate your real valued bandpass signal to baseband. However, upper branch picks up the in-phase component, and the lower branch picks up the quadrature component's real baseband. And here, since we are assuming DSB signal, due to this phase offset, we may have this unwanted sine and cosine factor. However, the other factors are the same. This is the idea in Costas receiver. Okay. Of course, we may have different things, but what is important is that here we have same M of t and cosine and sine. And what we do is that these are time functions with different gains. We multiply these two. Then we have message squared times cosine and sine multiplied, which becomes, as our trigonometric identity says, sine 2 theta. We want to minimize this theta. We want to make this theta 0. So if theta is 0, this branch output will be our signal. Of course, this theta is some theta of t with slowly varying error, phase error. And if this is fed and low pass filtered, which means that this is gone, then we have what? Some constant times sine 2 theta. And sine 2 theta can be well approximated by 2 theta for small theta, as you learned in high school math. So this output, if this output is bigger, then, for example, your frequency increases so that it compensates this theta of t. Or vice versa, depending on your choice of k. Got it? So this is a simple feedback loop that can remove the phase offset. The key is that you have same M of t. So this structure cannot be directly applied to single sideband case, where the upper branch and lower branch has different thing. If you remember, upper branch may have m of t cosine, but lower branch has m hat sine. So these are different. So you cannot directly apply Costas loop. But anyway, this structure not only can be applicable to the modulation of AM or DSP signal, but also for some FM signal. The details I'm not going to talk about. Okay, so let me resume. So this Costas loop is very interesting thing. It has application to the demodulation of DSP family, but also we can extend this idea to demodulation of angle demodulation. And the detail, I'm not going to talk about it because I'm not an expert to circuit. And the author of our textbook, using this opportunity to talk about frequency modulation, modulated signals demodulation. So he talks a lot about phase lock loops. And if you enter graduate school, you will choose which building you are going to live. And surprisingly, even though you may claim that you are a communications engineer, depending on the building you are living, you will see this PLL every day, or you will never see this PLL ever. That is quite interesting. But as I told you, wherever you go, okay, please be friendly with your classmates in other buildings, because you both must cooperate to make great advances, especially at this age of very, very specialized professional persons living. Got it? So sometimes, yeah, I'm not going to much talk about it. This is actually how frequency multiplier works. And as I told you, limiter generates a lot of harmonics. And if you pick second, third, fourth, fifth harmonic, then you actually, it's like you have built a frequency multiplier. But as you see that, this nonlinear filtering followed by some linear filter may have some distortion. And to remove that distortion, again, feedback is very, very useful. Right? That's what I want to say. Again, in the frequency divider, you see the feedback. Got it? Okay. Now, we are going to talk about why FM is preferred to the AM. Okay? So the story is all about interference. If you now remember correctly, in the early stage of radio communication, people already formed international organization where they set up the differences in their opinions about the use of spectrum. That is the kind of mother of so-called the ITU, International Telecommunication Union, which is now a part of UN. And this ITU conference is held every some year. And it was once held in Busan, Seoul, and other cities in our country, where the officers of other different countries come together and they settle up some conflicts about frequency use. So they usually divide the spectrum into several bands, and sometimes they subdivide the frequency bands into channels, and sometimes they say, okay, this is the band for TV, for example, analog TV broadcasting. Now, let me assign this one to South Korea and Japan. And unfortunately, Japan is very close, right? Even you can find more than 5 radio stations here in Pohang, the Japanese broadcasting radio stations, almost every time. Not only just strange day. So what do they do, especially for TV broadcasting? You have to remember this. Unlike acoustic signal, the electromagnetic wave is the transversal wave. What does that mean? If this is the direction of propagation of the radio wave, the physical quantity that is described by wave equation is orthogonal to the direction. The E field is orthogonal to the direction, and B or H field is also orthogonal to the direction. Unlike the radio wave, acoustic wave is longitudinal, which means that it makes the physical quantity increase or decrease to the direction along the direction of propagation. So as you see here, electric field may orient itself as a vector to this direction or that direction or that direction, any direction, depending on your transmitter antenna. So interestingly, if you have TV antenna long ago, that looks like, for example, like this in South Korea, then you have antenna 90-degree rotated in Japan, because this so-called polarization is very important. For this type of wave, is including electromagnetic wave and radio wave. Got it? So you make a lot of analogies between radio wave and acoustic wave. However, there is a huge difference. Radio wave, as a part of electromagnetic wave, it has so-called polarization. Anyway, even though this TV broadcasting band may be assigned to Japan and South Korea and assign different polarization, the problem is that this propagation environment of radio wave may tilt or rotate the angle of the polarization. What does that mean? If we have perfect orthogonality, interference will be very small. However, when the radio wave bounces or reflected, scattered, the polarization, so-called polarization discrimination factor, polarization discrimination is not perfect, which means that the signal interferes. So in some area of Busan, where I spent most of my childhood, there could be easily, we could easily detect Japanese broadcasting signal. So the so-called Jeonpasa owners, they have antenna on top of Geumjeong Mountain, one of the tallest mountain in Busan, where they could easily intercept the Japanese TV broadcasting signal. They had amplifier fed to the cable, and actually in my apartment just below the Geumjeong Mountain, I could watch Japanese TV, even 2 channels. So I watched Japanese animation around 2 or 4 weeks earlier than my friends. At that time, one of the popular Japanese animation movie was Galaxy Train 999, 은하철도 999. You will never know. But interestingly, the MBC broadcasted that Japanese animation every Sunday 9 a.m. So those children had to wake up early to watch 은하철도 999 every morning. And sometimes 2 episodes are just cut into and broadcasted 1 episode. So my friends approached me, "Hey, Junho, have you already seen Japanese the episode already?" And I said, "Yes." And oh, what happens? So the problem was that I couldn't speak and understand Japanese, but I could just see and guess, and I could tell my friends the story about that. Anyway, let me go back. The signal, radio signal, interferes. As I once told you, within a short range, cable is much better. However, if you connect the same cable, the output exponentially decreases output power. However, in radio propagation, even though very close to antennas may have huge attenuation, like 20 dB, 30 dB, 50 dB. However, that does not afterwards decrease much faster than cable, even though it propagates 100 kilometers. Because in free space, we know that the power decreases 20 dB per decade. Right? What does that mean? If the distance becomes 10 times, then you have a 20 dB decrease. Next 10 times, 20 dB decrease. So 100 times difference just give you 40 dB difference. Got it? So the radio signal may be weak, but my signal is also weak. Desired signal is also weak. And the interference may interfere and cause a lot of trouble. That's why this international organization became very important. And they still have conferences regularly. And this is a very, very big conference. Still, they talk about what kind of services must be provided by 6G cellular telecommunication. They decide. Got it? Anyway, so these are the analysis of some the cases of interference present in the received signal. And I just talked about the context of why we have to talk about interference in radio communication. And the detail will be provided from next class meeting. Okay, that's all for today.